All right, so the next section deals with matchings and Alright, so the next section still deals with matchings and independence in graphs. We're just going to extend the ideas that we formulated in the previous section. So recall Tutt's one-factor theorem. The theorem said that a graph G is a perfect matching. What's a perfect matching again? It's a matching where every vertex is incident with every vertex in the graph is incident with a matching edge. So in other words, I mean, obviously, if a graph is odd order, you're not going to ever find a perfect matching because there's always going to be one vertex that's unmatched. Now, here, a graph is a perfect matching if and only if for every subset of vertices in the vertex set of G, if you remove this subset from G and you count the odd components, that is at most the number of vertices within the set S. And that has to be true for every subset S of G. So that's a characterization. So whenever you've got a set where this inequality breaks down for some set S, then you don't have a perfect matching. Now the question is, what we want to do is we want to try and go and count the number of unmatched vertices. So the question now becomes, so in other words, if the graph doesn't have a perfect matching, in other words, we can find a set S for which the number of odd components of G minus S is bigger than the coronality of S. Then does it mean that there is no matching that is close to being perfect? So in other words, we sort of want to know how many vertices are unmatched within a maximum matching. So in this example here, every matching in the following graph leaves at least two vertices unmatched. Now, how would we determine that? The graph, and what we're going to do is we're going to delete the vertices V1 and V2. Right. So there we've got four odd components. So within each one of those components, I cannot find a perfect matching, right? So there's always going to be a vertex in each component that will be unmatched. Now, so if I look at a maximum matching within the graph G, right, so how this is going to work is there's going to be, without loss of generality, say there's going to be a vertex within this component that doesn't have a matching partner. Let's say it is this vertex here. So I'm going to have to find a matching partner for it. So I can use V1 or I can possibly use V2 as well. Without loss of generality, I can use V1. Then within this component here, there's going to be an unmatched vertex. So the only vertex I can match that unmatched partner to is V2 then. But now I've already used V1 and V2, so I can't match that unmatched partner there because I've already used it, and I can't do it there. Okay, so what happens in this case is that there's going to be two vertices that are going to have that I'm not going to be able to match. Right, so the same is true for the same is true if you take any two components of the four odd components. You can find two matching partners for the unmatched vertices in the component. So in total, how many odd components are there? So if you were to count the odd components, and S is the set of vertices V1 and V2. We counted 4. Okay, of the four odd components, they are all going to have one unmatched vertex, and I can match the unmatched vertices to V1 and V2. So there's still two left that I have to match. which I'm not going to be able to match. So that's going to be the number, any maximum, any matching of the graph G is going to have 4 minus 2 unmatched vertices, always, okay. So it's going to have at least 2 unmatched vertices. Right, so again, what I just described is given here in this proof here. So there I'm removing the set S, and if you take a maximum matching, you look at the odd components, there's within each odd component there's going to be an unmatched vertex, and we need to find a matching partner for these unmatched vertices. In total there are going to be 4 unmatched vertices, and I can only use the set that I remove to find a matching partner for that, for all those unmatched vertices. But I've only got 2 at my disposal, but I've got 4 unmatched vertices. So of the 4 unmatched vertices, I can only match 2 of them to the set S, because the set S is coronality 2. So therefore, I'm left with a I'm left with 2 unmatched vertices. Okay. So that whole idea brings us to Berger formula. Now remember this alpha prime of G, that is the coronality of a maximum match of the largest possible matching in the graph G. Right, so if G is as order n, then this number is basically the smallest possible value for this quantity here. And what's that quantity? It's basically the number of vertices plus the coronality of S minus the number of odd components of the graph G without S. And you basically let S run through the whole of G, and you pick the S that will give that will make this value as small as possible. So you can also see it in a different way. You can see it as any maximum matching is going to leave it's going to leave this number of vertices unmatched. The maximum of k, the odd components of k minus S vertices. So you need to run through S and find the maximum possible value of that. Right, so just viewing it this way, if I look at this quantity here, okay, now how do I make this quantity the smallest possible value? You take this quantity here, which is the same, and what you do is you make it the smallest by making this difference the largest that it can possibly be. Right, so the minimum of, or the minimum of that occurs where basically we have the is where we basically have the maximum where S runs through the whole of V of G of this quantity, which is the difference between the number of odd components and the cardinality of S. So in the previous example, we did the same. We took the number of odd components, and from that we subtracted the cardinality of the set S that you're removing, and that will count your number of unmatched vertices. So basically, any maximum matching will leave this number of vertices unmatched. Right. So to prove it, we first prove that inequality. Now we take S to be a subset of the vertex set of G, and we take M to be a maximum matching. Now, as above, at least K's, the number of odd components of G minus S vertices remain unmatched. And why is that? Because again, think of the previous example. We took the number of odd components. Each one will have an unmatched vertex. And from that we subtract the coronality of S. That'll count the number of unmatched vertices. Remember? So that is how many unmatched vertices we will have. Now, we're assuming now that G doesn't have a perfect matching. So there will exist sets where the odd components of G minus S minus the coronality of S will be at least 0. Right, so in the maximum matching, counting the vertices, so there will be, in a matching of coronality M, there will be how many vertices at play? Right, there will be, okay, so if I count the number of edges there, that's going to be M edges. And if you count the number of vertices, you're counting how many? You're counting two M vertices, right? So 2M will be exactly equal to 2 times alpha prime of G, which is coronality of the maximum matching. That will be at most the number of vertices minus the number of unmatched vertices. So you're gonna have in this 2M matching, you're gonna have your matching, and then what's going to be left is your set of unmatched vertices, which call it that. So you're going to take the total number of vertices, and from that you're going to subtract your unmatched vertices, which is that. Okay, and that is going to count. That's going to provide an upper bound for that. Okay, so therefore, dividing by 2 on both sides, we have the upper bound there. How do we make this value? How do we make that upper bound as small as possible? Because we want to find the best upper bound. We make it as small as possible by basically by making this, by maximizing, or rather by minimizing that value, and we get that by maximizing that, choosing the S that maximizes that. And the S that's going to maximize that is going to minimize this. Right, so that yields the upper bound. So now we need to prove this side of the equality to get equality there. Okay, so again, how do we do this? We show that G has a matching of this coordinality. We show that G has a matching of that coordinality, and if it does, then any maximum matching will have coordinality at least that. Okay, that is what we want. That's what we want to do. So let's take P to be this maximum value. Now they say, recall the example that counted the number of unmatched vertices for this particular set S. We take the number of odd components, which all those components will have this number of unmatched vertices, and from that we subtract the number of vertices in the set S, and that will give us the number of unmatched vertices. Now this value p, that's the largest value that I choose. Now if p is 0, if p is 0, then this value here, if that value there can be 0, which means that the number of odd components of G minus S is equal to the number of vertices in S. If P is now the largest value that this thing can take on, and again, if this takes on a negative value, it means that the coronality of S is bigger than or equal bigger than K0 G minus S. And if that value takes on zero value, then it means the coronality of S is equal to the number of odd components of G minus S. So therefore, we have this inequality that holds for all S. And in that case, G is going to have a perfect matching. It's going to have a perfect matching, and so this that inequality holds. That inequality is going to hold because then this thing here falls away, which is, it's going to have a 0 value there, and so any maximum matching is obviously going to have, if it has a perfect matching, it's going to have n over 2 matching edges, obviously. Okay, so we basically we need only to consider the case where P is at least 1. Right, so to carry on now, what we're going to do is we're going to do a little bit of a construction here. We're going to take G and we're going to add a complete graph to it. Look at the definition of addition of two graphs, right? So you take both graphs and you join each vertex in the one graph to every vertex in the other graph. So we're going to form this construction. We're going to take G and we're going to add a complete graph on P vertices to it. Now we're going to take this G prime and do the following. Right, so there's a quick illustration of the graph G prime. We take whatever G is and we take K, the complete graph on P vertices, and we join each vertex in G to each vertex in KP. Now I'm going to show that this graph G prime has a perfect matching. Right, if I can do that, let's say I can show that this graph is a perfect matching M prime. Then we can find the matching of desired coronality. Now what's going to happen is if we delete the vertices of KP from G prime, we're going to destroy at most P edges of the matching M prime. And I'll explain why that's the case, right? Back to your sketch, right? So you've got this matching M prime. Now if I'm going to delete KP, right, how many edges of the matching am I destroying? The matching is now all the blue edges. Right, so at the very worst, right, you can have an edge of the matching that matches each vertex in GP to a vertex in G. Right, so how many such matching edges can you have? You have at the very most you have P such edges, right? So you either have that situation, or you could have this situation where you've got a matching edge there. You could have more than one such matching edges. I'm just doing one example here, and then you can have for the remaining vertices, you could have matching edges there. Okay, so in total there how many matching, just as an example, how many matching edges do you have there? You've got P minus 2, which is pretty much going to count these matching edges there. And then you've got one matching edge there. So you're adding plus 1 there. So it's pretty much P minus 1 in that specific case. So, right, so basically, worst case scenario here is you're going to destroy at the very worst P matching edges. Okay, so as soon as you, as soon as you have matching edges here, then you're going to destroy at most P, well, you're going to destroy fewer than P edges. And if you've got no matching edges in that area there, you only have matching edges between between vertices and P and P of KP and vertices of G, and then that is the extremal case where you delete P matching edges. Right, so in that case, you at the very worst, you're destroying from M prime, you're destroying P edges, and that is going to leave a matching M of G, which is going to have coronality at least, the coronality of M prime minus P. Now, we assume that M prime, we're going to prove that M prime is a perfect matching. So it's going to have N plus P over 2 matching edges minus the P that you destroyed. And adding that is going to be that N minus P over 2. And we define P as that quantity there. And that maximum value is going to basically be the one that minimizes this thing here. And that's a coronality I want. So all I have to do is I just have to show that this constructed graph has a matching, or has a perfect matching. Right, so that's all I need to do to prove my result. So let's suppose to the contrary that G prime has no perfect matching. Okay, so by Tut's one-factor theorem, there must exist a subset S prime of the vertex set of G prime, where this inequality holds. The number of odd components of G prime minus S prime is at most the coronality of S prime. Now, they say here that the vertices of KP must be contained in this set that you're removing, since otherwise G minus S prime is connected. But let's say this S prime, let's say S prime lies there somewhere, okay? Now if you delete, that's going to be S prime. Now if you delete S prime, the graph, resulting graph is going to be connected, right? Because we've still got all those vertices and they are joined to any remaining vertex outside of S prime. So the graph is going to be connected. If S prime, say, lies partly in G and in KP, then again partly in G and partly in KP, then again removing it, your graph is still going to be connected, because you're going to have a vertex there that's going to be attached to every vertex there. So that's going to be still connected. Okay, so if G minus S prime, if this set that you're deleting does not completely lie in S prime, and now I apologize that that you should just delete those signs there. Right, so basically, okay, so now if this is not the case, then G prime minus S prime is going to be connected. And that's going to give a contradiction. Why? Because then if the number of odd components of the graph that you get by taking G prime and deleting this set S prime, whatever it is, you can have, because the graph is connected, the graph is going to have one component. At the very worst, that one component can be an odd component. So the number of odd components is at most 1. And the set S prime that you're deleting has coronality at least 1. And that is going to contradict the assumption that we made there. So therefore, this set that you are removing it absolutely has to contain all the vertices of VKP. Right. So what is S prime? So S prime must be all the vertices of KP together with a set S subscript 0, where this S subscript 0 lies within the vertex set of G. So as an illustration, this set S prime must contain all the vertices of KP. Right? It must contain all the vertices of KP, and it could possibly contain a small section of G as well. So that small section of G, we call that S subscript 0, and the rest we call V of KP. Right, so let's work out the coronality. This coronality, the odd components of G prime minus S prime, it's going to be the same as the number of odd components of G minus S 0 minus the coronality of S prime, which is going to be coronality of S minus, coronality of S0 plus P, and you take the minus of that. Going back to the sketch, if I basically go and I delete all of that, then whatever remains is going to be what? It's going to be this section here that remains, and that section there, the number of odd components, the number of odd components of G prime minus S prime is going to be exactly the same as the number of odd components of G minus S 0, which is basically the number of odd components I get in that section of the graph once I've deleted this whole set here. Then, so back substitution, we know what the value P is equal to, and we replace that with the maximum of that. Now by inspection, you can see this is going to be bigger than that. Okay, because again, this quantity here, I'm looking at the S that's going to maximize it, and this is just the same quantity where I choose S to be S0. And here I'm choosing the maximum where I let S run through all of the V of G's. So this is at most 0. Right, and that's a contradiction because we said that the reverse is true. The odd components of G prime minus S prime is at least the coronality of S prime. Okay, so next we've got another nice little application of Tutt's one-factor theorem, and it's called Patersons theorem. If G is a bridgeless cubic graph, what's a cubic graph? It's a graph where every vertex has degree exactly 3. Then we say that G has a perfect matching. Alright, so we're going to apply Tutt's one-factor theorem. So we're going to choose a subset S of the vertex set of G, and if we know that if G minus S has no odd components, right, then we know immediately that the number of odd components of G minus S is at most the coronality of S. So essentially, to use Tutt's one-factor theorem, we need to just show that this is true. Remember that for every subset S of the vertex set of G, proper subset, we have that this is true. So that is what we want to prove for every arbitrary proper subset S of G. Okay, now if the graph has no odd components, then we're done. So we may assume that G minus S has at least L odd components. And let's call these odd components G1 up until GL. And also let EI be the set of edges joining the ith odd component to the set that we remove. Now we are going to just show that the number of edges between the ith odd component and S is at least 3 for all the odd components. So there's just a little sketch there. This is the set S of vertices that I'm removing, and again, right, this is going to be that's going to be the edges between G1 and S. That is going to be the set of edges. So there we've got my set S of vertices that I'm removing. Here the G's are my odd components, and here is that's the set of edges between S and G1. That's going to be the set of edges between S and G2. That's going to be the set of edges between S and G3. And that is going to be the set of edges between S and GL. Right, now my aim is I want to show that this is true. The number of edges, the coronality of each one of these E sets is at least 3. Right, now we know that G is bridgeless. Okay, so we have that the number of edges between the ith odd component and S is at least 2. Going back to my sketch, you can see E2, if there was only one edge between the vertices of G2 and S, you would immediately be able to, that would be a bridge, right? So you need to have, obviously, at least you need to have at least two edges there. Right, so let's prove now that it must be at least 3. So let's suppose there exists a set EI where the coronality is exactly 2. Right, now let's see what happens if 2 edges in EI are incident with the same vertex. Well then, GI has all vertices of degree 3 or 1, and thus of odd degree. Right, so again, let's see what happens there. Okay, so remember, we're assuming that 2 edges, the 2 edges in E2 are incident with the same vertex. You've got that, or you've got that. Okay, so quickly look, if G2, in this case, where there's two edges that in E2 are incident with a vertex in S, then it looks like that. And so what's going to happen is G2 will have degree 2 vertices. If I delete that, those are going to have degree 2 vertices, and it's going to have the remaining vertices are all going to have degree 3. Let's see what happens in this case. Okay, so basically, if we look at the, we know that twice the number of edges of G2 is going to be the sum over the degree sequences of the vertices of G2. Right, so we have 2 vertices that have degree 2 and all the others have degree 3. Right, so that's going to then become 3 times the order of G2 minus 2. And the order of G2 is odd, so we can replace it with 2k plus 1, where k is some integer, a positive integer, right? And that is then going to imply that we are going to have, that is going to be 6k plus 3 minus 2, and that is going to be 2 times 3k plus 1, which is going to be odd. And that's a problem because you can't have an odd number equal to an even number. Okay, so that can't happen. Right, let's see what happens if 2 edges in E2 are incident with the same vertex in G2. Then G2 has 1 degree 1 vertex, and in G2 minus 1 degree 3 vertices. So let's quickly see what happens there. G2 has 1 degree 1 vertex, and in G2 minus 1 degree 3 vertices. That's going to imply that, right, again by the edge formula, the size of twice times the size of G2 is going to be the sum over the degree sequences. And that's going to add up to 1 plus 3 times the number of vertices of G2 minus 1. Okay, and because the order is odd, we can replace it with 2 times an integer k plus 1. It's going to add up to 6k plus 1, which is an odd number. And an odd number cannot be equal to an even number, so that's also impossible. If we go back to the sketch here, the only other possibility for this E2 is that you have a situation where the edges are the 2 edges that you have, they don't go to the same vertex in either S or G2, so that happens. Now, in this case, if I look at G2 on its own, and I go and delete these edges here, if I go and delete the edges in E2, if I go and look just at if I just go and delete those edges there, my graph G2 is going to have 2 vertices of degree 2, and again it's going to have in G2 minus 2 vertices of degree 3. And we already looked at this case, and I'm not going to look at that case again. It's the same one we considered. So therefore, we have then again that it cannot happen. Not one of these cases can happen. So you cannot have 2 edges that are incident with the same vertex in either S or G2 or GI in general. Again, if they are incident with different vertices, then 2 in GI are going to have degree 2, and the remaining vertices are going to have degree 3. So we already looked at that case. That's going to contradict the handshake lemma, which is sort of what we did just now. So each EI must have at least 3 edges. So addition of these inequalities. So let's go and count the number of edges. What I want to count is, I want to count the number of edges between S, between the set S and the set of vertices between my GIs. Right, so the number of edges between S and V minus S is going to be at least, and it's at least there because you could still have some even components as well. So the number of edges between S and V minus S is going to be at least the sum of all your edges in each E. And that is going to be at least 3L. Okay. Now on the other hand, we have that the number of edges between S and V minus S is going to be at most 3 times S. And why is that? If you look there back at our sketch now, so each vertex could have 3 neighbors in V minus S, and that is the maximum possible number of edges. Because remember, you could still have even components as well. I mean, that doesn't really make a difference, but the largest number of edges you can find between S and V minus S is 3 times S. Right, so we said that thing there is at least 3L. So 3L is at most 3S, so L is at most S. So the number of odd components of G minus S is at most S. So by Tut's one-factor theorem, the graph must have a perfect matching. Right, so if a cubic graph is bridgeless, then it is going to have a one-factor. Okay, so this condition that G is bridgeless is essential. You'll see the following example. The graph has bridges, but it doesn't have a one factor. So in fact, the graph actually has 3 bridges. It's got 3 bridges, and it doesn't have obviously it doesn't have a one factor. Interesting question would be to ask that, well, this graph has got 3 bridges. The obvious question is, can I maybe prove the result is true for a graph that has, say, 1 bridge or 2 bridges? And that's a good exercise to go and do. Right, so this brings us to independence and the independence number of a graph. We say a set S of vertices of G is independent if no 2 of them are adjacent in G. We already did that definition. And again, the largest coronality of an independent set of G, that's called the independence number of G. And it's denoted by alpha of G. So alpha prime of G is a coronality of maximum matching, right? So it's the largest number of independent edges. And alpha of G is the largest number of independent vertices. So if you just look at this graph here, which is a path, it has independence number 4. The blue vertices denote an independent set, and that's the largest independent set that you can get. Okay, so another definition, if a vertex and an edge are incident, then they cover each other. Right, so a vertex cover is a set of vertices that covers all edges in G. Alright, so a vertex cover is a set of vertices that covers all edges of G. And likewise, an edge cover is a set of edges that covers all vertices. Okay, so note the difference between the two. So the minimum cardinality of a vertex cover of G is called the vertex covering number, and it's denoted by beta of G. Likewise, the edge cover of G edge cover of G is its edge covering number, minimum coronality. And that's denoted by B prime of G. So if you look at the path again, we said that the vertex covering number there is going to be 3. Remember, vertex covering is the smallest. Well, the vertex cover is a set of vertices that covers all the edges. So I want to cover all the edges, so I mean I can select that vertex there. I can select that vertex there, and I can select that vertex there. Clearly, all the edges are incident with at least one of the 3 vertices there. So that is that's an edge. That's a vertex cover. Now, can I get by with 2 vertices? And the answer is no. I can't get by with 1 vertex or with 2 vertices. So the vertex covering number there is going to be 3. Then the edge alpha prime, which is going to be the matching number. And that is going to be again, I can pick a edge there, I can pick an edge there, and I can pick an edge there, and that's a coronality of the largest coronality of a matching is going to be 3. I can't get by with more than that. And then looking at B prime, which is the edge covering number. So I need, how many edges do I need? Or rather, the smallest number of edges that I can have to cover all the vertices. Right, so there's a... Right, so if I take that 3 edges there, I'm still left with a vertex that's not covered. So I'm going to have to include a 4th edge there. Now I cannot get by with 3 or fewer edges. I'm always going to have an uncovered vertex. So the edge covering number there is clearly 4. Okay, so as an example, you guys, as an exercise, can go and try and work the independence. The independence number for a complete graph is quite straightforward. That's very easy to work out, and the vertex covering number for k, the complete graph, is n-1. Pretty straightforward to work that out. You can prove it by just showing that that a set of n-1 vertices is definitely going to be it's going to cover all the edges, and then you can just show that if you've got any set that's got fewer than n-1 vertices in it, you're going to have an edge that's not going to be covered. It's quite easy to see that. And then alpha prime, the matching number of kn, that's quite obvious that it's the floor of n over 2. Okay, and to prove this here, the edge covering number, you just produce an edge cover of that coronality there, and if n is even, it's easy to do because you just take a perfect matching, and that is a edge covering of the required coronality. And if n is odd, then you just take a matching of coronality n-1 over 2, and then you just have one more unmatched vertex. So you want to cover that vertex by just including one edge, and that then becomes n+1 over 2, which is basically the ceiling of n over 2. That's if n is odd. Then you prove basically that this has coronality at most n over 2. you can then prove that any cardinality or any number of edges that's smaller than that is definitely not going to cover all the vertices, and that's also easy to see why that's the case. Okay, the next result here is this observation, and that is the observation that a given set S is independent if and only if the complement of this set is a vertex cover. So for argument's sake, let's assume that S is independent, and let's quickly then prove that the complement is a vertex cover. Okay, so let's assume S is an independent set, and we want to now show that the complement is an edge, or the complement is a vertex cover. Okay, now how do we see that? Well, let's assume V minus S. Let's assume V minus S. So let's assume V minus S is not a vertex. Is not a vertex cover. Now, what does this mean? It means that if it's not a vertex cover, it means there's an edge that is not covered. So there's an edge that's not incident with any one of the vertices in V minus S. Right, so the only place that this edge can lie is it must then lie between two vertices in S, which is impossible because S is independent. Right, so that definitely V minus S is a vertex cover. The reverse, let's assume V minus S is a vertex cover, and now we need to prove we need to prove that S is independent. Now, if S is not independent, then it means there's an edge in S there's an edge between two vertices of S. But the problem now is V minus S is not going to be a vertex cover simply because this edge is not covered by the vertices here. In other words, the red edge is not incident with any vertex there. So it's easy to see there that S is independent if and only if V minus S is a vertex cover. Right, so the corollary from this little result is that the independence number plus the vertex covering number is always equal to n, the number of vertices. Right, and the way to see that is you pretty much take S to be a maximum independent set of G. Then V minus S is going to be a minimum vertex cover. Right, so if you take a maximum independent set, that set S is going to have cardinality alpha of G. And if you sum that with the vertex covering number, then the cardinality of S is at least that. And remember now, we said that the set V minus S must be a vertex cover, and B is the smallest vertex cover. Or B is the cardinality, beta is the cardinality of the smallest vertex cover. So therefore, alpha plus B, beta of G is going to be at most, it's going to be at most the cardinality of S plus the cardinality of V minus S, which is the cardinality of V minus S, and that adds up to N. Right, so now take a set S. Right, so let's take let S be a vertex cover. Such that the cardinality of S is this vertex covering number, then if we look at the vertex covering number of G plus alpha of G, we know that that is at least the coronality of S. Now remember, what do we know about the set V minus S by the previous theorem? V minus S is an independent set. And what is alpha of G? Alpha of G is the coronality of the largest independent set. So alpha G has coronality at least the coronality of V minus S. Okay, so that is going to imply that's the coronality of V minus the coronality of S plus the coronality of S, which is at most alpha of G plus beta of G, and that part there is equal to N. Okay, so N is at most alpha G plus beta of G, and we also said that N is at least alpha of G from previous reasoning. So therefore we need to basically have equality.